Okay, so let's do some correlations in R. So if you haven't gotten the data yet, grab it, set your working directory, load the data, check out, ooh, this should be statslab08.csv, not statslab07.csv. Let's attach the data. We're going to do something a little different this class. I don't like it this way, and I'll talk about why in a minute. But some of you might like this a lot. So entering the following commands, str data, consistently, you know this. What do you see?
Information.
Information. You see what variables there are, right? You should see like IV, dv1, dv2, dv3. All right. So that tells us what is in something. What something is. So it should say that it's a data frame. Now, if you type in IV, what do you get? Nothing. You should get an error. Good. Okay. An error is not nothing. It's something. Error. Object IV not found. Right. Now do this. Attach data, and then type in IV again.
Values.
Now you have values. Those values in IV, where do they come from? They come from the data frame. Previously, when we were doing ANOVAs and things, we said, okay, let's use these variables, and they're found in this data frame named data, or whatever we had to name. But here what we've done is we've attached data. You should have 30 numbers. If you do length IV, it should be 30. So if you attach a data frame to R, you can use the variables directly. And this can be kind of helpful because you don't have to do anything like data, $, variable. You just say the variable name. But the warning, this is the reason I don't like to do this. So if you've been working in R for a while, it's not a brand new like session. You know how it says like, would you like to save your session? If it's not a brand new session, you might have a lot of variables and things that you're working with that you want to work with later. If you attach a data frame, what will happen is if there are any variables in the data name that have the same name as variables that you already have, the variables in the data frame will wipe those other ones out. They'll be gone. This is why I don't like to attach data personally, because you run the risk of destroying stuff that you might use. But for most of you guys, you're not doing big, long data analyses with lots of different parts. You're doing homework with a couple different things. So maybe attaching it is okay. I want to talk a little bit more about working in R. So on the test, like there were lots of people that didn't even do the section for R. They did the first part, and then they didn't do anything for the second part. I was really surprised. Like, you didn't do anything. So I asked for the emails, and you guys have sent me some emails back. And some people say, like, I don't understand R. I don't know how to work with R. And I'm not sure, like, what the problems are with working in R, because I've tried to go through things individually. But let's talk just a little bit more about working in R. One, you can name variables almost anything that you want. So I like to abbreviate things. The variables in that data frame, IV. What do you think that stands for? Do I have it up there? Yeah, okay, it is. Independent variable, IV. Oh, that makes sense to me. On some of my R code, you see things like UVAR. That means unbiased variance. And other times I've just said like V1. Meaning like the unbiased variance for sample 1. So originally when we were talking about variance, like we had to differentiate between the biased and unbiased. And we still could be doing that differentiation, but almost everything that we're going to do right now involves using unbiased variance. So from now on, if you look at my R code, you might see things just like V, which means the unbiased variance. You know, you do not have to do this when you are doing homework or if you are making notes for the exam. If you get confused because I say like CV1 and this B that and it's confusing, what you can do is you can go through and name things differently. So if you don't like IV, you can name it the independent variable. You can name it my independent variable. You can name it whatever you want. Name it whatever makes sense to you. Okay, let's talk a little bit more about data frames. For a lot of the homework assignments involving like computations, t-tests and ANOVAs, and even the correlational homework that we're going to be doing for tonight, the data that you're going to analyze is going to be inside of a data frame. So you need to get that data out of the data frame. And there are lots of ways that you can do this. But one thing also that I want to mention, on the test, so I had some data frame, and in that data frame, it contained variables, and the names of the variables were test, breakfast, sleep, incentive. There was something else. There was something else. And then I would ask questions where I didn't necessarily use the name of the variable. I didn't say model test as a function of sleep. I didn't say that. Instead, I'd say something like, see if there's a relationship between the test scores and whether or not the participants ate breakfast. So if you did that stir data, you would see, okay, stir data shows me that we have data frame and we have something called test and it has numbers in it. And we have something called breakfast and it says yes or no. And we have something called sleep and it says more or less, right? So when I asked you this, I didn't say model test, or I didn't give you the model. I could have given you the model, but part of the test is to see if you understand how to build the models. So I could have said, do this. Test as a function of breakfast. Right? But when I went around the room, I saw lots and lots and lots of people saying this. Scores is a function of length. Which was something that you needed to use for a homework. But that was when you were dealing with a data frame that had a variable called scores. And there was another variable that was called length. And the data frame and the test, it didn't have those variables. So you do your model, and the ANOVA says like, sorry, error. It's because they didn't exist. So if you try something and it doesn't work, do that stir dot, whatever you name the data frame. You don't have to name it data. You can call it my data or my awesome data frame for the best statistics class in the world. And look and see what's there. And look at the question and think, okay, relationship between test scores. We have incentive and sleep and test and breakfast. Which of those would be the test scores one? Test, then it's probably it. Breakfast, oh, that must be breakfast. Then you got it, no problem. All right. I try to make my variables name something that's fairly obvious, or I give it to you. Like I told you, use S2, right? All right. So we need to get information out of the data frame. One thing that we can do is we can use information in a data frame directly by saying something like this. We give it the data frame name, the $sign, and then the variable name that's in that data frame. We've done this earlier in classes. We've said things like my variable is equal to data, and then, I don't know, S1, right? We've said things like that, where we are using this directly. Data frame name, $, variable name. Instead of using it directly, because typing this in is a real pain in the butt if you want to do it multiple times. You can save that with your own name, which is what I just did. You can name it whatever you want. It's a variable. You can name it anything that makes sense to you. whatever you want, equals the data frame name that you're working with, and the variable name that's in the data frame. Okay, you can also, like what we just did, you can attach the data frame and use the variables directly. Just attach. And then you don't have to say data frame name, variable name. You can just say, you can just say variable name. And work with that automatically. Like you guys just did, right? You typed in IV. That was the variable name. And it told you what IV was. Okay. So, there are a number of ways that we can do an ANOVA using those different methods of accessing data within the data frame. So if we don't have an attached data frame, we can do something like this. Analysis of variance, we're going to model our dependent variable name as a function of the independent variable name and tell it where those independent and dependent variables are. They're in that data frame, right? Or we can say in the dependent variable name in the data frame is a function of the independent variable in the data frame, and then we don't have to say the data frame name again, because we've already told it where these data are. I don't like this. This is long, really long. And if you have lots of variables that you want to look for the interactions between and things like that, this can get really, really long. Okay. If we have an attached data frame, if we attached our data, we could do something like this. ANOVA dependent variable name as a function of our independent variable name. And this is basically just this without specifying the data frame at the end. Why don't we need to specify the data frame name at the end? We've attached the data frame. It can get those variables directly. The only reason that we had to specify this up here is because we didn't have those variables loaded into R by themselves. They were buried in the data frame. Okay. You can also do it with variables saved with your own name. So if you did something like, oh, my independent variable equals the data frame name $ independent variable, then you can do it like that. ANOVA, whatever you name the independent variable as a function of whatever you named the dependent variable. And you won't need to specify the data frame for that either. So, if you don't understand R, or how to work with variables, like add two variables together, come and talk to me, because it's important. A big part of statistics is not just understanding what the statistics are, but actually doing some statistics and running t-tests and doing ANOVAs. And most of you are doing the t-tests and the ANOVAs, but a lot of you aren't. So if you aren't, and you don't understand what you need to do them, come and talk to me. Okay, so let's visualize some scatter plots. Go ahead and do this. Plot IV, comma, DV. A positive correlation. It's a perfect positive correlation, right? We see something like this. So a bunch of dots. And down here you see IV, independent variable, and DV, our dependent variable. So we're basically plotting independent and dependent variable scores. Each point on this is showing you the values of both variables at the same time for one pair of the observations. So it would be like I was measuring her. Okay, what's your IV level? What's your DV level? Sorry, what's your independent variable level? What's your dependent variable level? Maybe it's something like height and weight, right? So does weight go up as height goes up? So I measure one person's height, I measure their weight, and each point would then indicate their height and their weight. Okay? So, a couple of you have already said that this is a perfect positive correlation. And it certainly looks like what a perfect positive correlation should be, but we should probably test this. So let's check. So, don't do this. What am I doing? n is equal to the length of the independent variable. The independent variable, the length of the independent variable and the length of the dependent variable, whatever it is, should be the same if we're doing a correlation. Okay, so I'm getting n, which is like the number of pairs that we have, right? We have one IV and one DV for each person, subject, whatever that we were looking at. So then I got the mean of the independent variable and the mean of the dependent variable, and I got the standard deviations of the independent and dependent variable. When I do this, SD, IV, what type of standard deviation does that give me? It's the one based on the unbiased variance estimate, right? Okay, so then I have IV minus MI. So that is each score in the independent variable minus the mean of the independent variables. So I'm calculating differences for our independent variable. Then I do exactly the same thing for the dependent variable. So then we need to calculate covariance, right? Because we can calculate the correlation if we know the covariance and the standard deviations. We have this, we don't have the covariance yet. So what do we need to do? We need to multiply the differences. Each difference with its paired difference for the other variable. So that's what I'm doing here. Products. Products equal the differences for the independent variable times the differences for the dependent variable. So then the covariance is the sum of those products divided by n minus 1. Right? Okay. Then correlation is the covariance, CV, so I'm abbreviating, but you don't have to do that. You could say covariance. You could say unbiased standard deviation for our independent variable and have some ridiculously long name if you like. Okay, so let's do this. I'll do this. You don't need to do this. Okay, let me copy. Copy. Go into R, paste, and now I will copy and paste this. So this is how you could have solved problems 18 or 17, 18, or what? 18, 19, and 20 on the homework, I think. All right. So if we look at covariance, that was 589 and change, and the correlation was 1. It should be 1, right? We had everything following on a line, whereas one thing increased, the other thing also increased. So it should be a correlation of 1. All right, so that's the long way to do it. Now let's do a shorter way to do this. So this is what we found. Do that. So when you did covariance, the independent variable and the first dependent variable, you got exactly the same thing. When we did the correlation, you got 1. Sweet! It's easy. I wanted to go through the calculations by themselves so you could see that we actually are getting what we should be getting. But now that you know that it works, you can do this for most of the questions. I might ask you something like, what could the maximum covariance be for a linear relationship between two variables with these standard deviations? It's the two standard deviations multiplied by themselves, right? All right. So that you'll probably still have to cover. But if I just ask you for covariance, there it is. Correlation, there it is. Okay, so let's take a look at a different correlation. We use our second dependent variable for this set.
Negative, perfect.
It's a perfect negative correlation. So you should see something that looks like this. Mine is a little bit different from yours because the code that I use specifies different parameters to make this look better. We should have something like that. So what's the covariance? I just did it. It's minus 589. It's the negative version of what we had last time. Minus 1. So everything's basically the same except for the signs, right? All right, how about this? Let's do it for the third dependent variable. We have a positive relationship, but it's not a perfect positive relationship. Looks something like this. Now, generally, as we increase in x, we are increasing in y. Now, this doesn't happen for every single case, so here we have a particular x and y, and as we increase in x here, we actually observed with this person a decrease in y. But in general, as you go up in one, you will go up in the other. This means, what about the correlation that we should be finding? It should be positive. And based on the way that these things are spread out, this should be a fairly strong positive correlation. So covariance, did you find 634?
Yes.
Cool. How about correlation?
Very close.
0.96 something? Okay, great. How about this? For the fourth dependent variable. Not strong. It's positive and not strong. It's a weaker positive correlation. This is actually still a pretty decent correlation. But it is weaker than what we had before. So we still seem to have this general tendency to increase. As x goes up, y tends to go up. There's a lot more spread, right? Things are a lot more scattered. That must be why they call it a scatter plot. Shows you how scattered the data are. Okay, so what's the covariance? 622 something?
Yeah.
And the correlation?
0.85.
0.8 something? That's weaker than what we had before, right? It's still a strong correlation, but it's weaker than what we had before. Okay, how about for our fifth dependent variable?
Weaker.
How do you know? Have you already looked at the weaker? It's a positive correlation, but it's weaker than what we had before. It's getting to the point where you actually have to think about things, because it's, at least for me, when I look at this, it's not like boom, oh, we have a positive correlation. To me, it looks all sort of spread out. But yeah, generally, I guess you sort of have this increase, right? As x goes up, y tends to go up, but things are a lot more scattered about. So the covariance was what? 554. And the correlation was what? 0.61. Okay, let's go back and take a look at these different correlations really quickly. So let's start with the first one. Okay. So the first one, we had something that we could just describe with a straight line, right? We wanted to create like imagine a bubble or something that creates all those, or that contains all those points. It's this very thin type thing. When we got to the weaker one, still very strong, instead of it being just a line, now we sort of have to draw this ellipse if we want to contain everything, right? And as we go to the next one, this gets bigger. And as we go to the next one, So what's happening? As the correlation is decreasing, like, it's like we're blowing up a balloon. What, you know, it's flat and then it starts getting bigger and bigger and bigger. And what would this look like, you think, if there was no correlation at all?
Circle.
Looks something like a circle. Sorry. I'm no artiste. Let's take a look. So here is no correlation. Go ahead and plot it for yourself. Find the covariance.
Minus
0.5.
So negative 0.15 for the correlation. How about the covariance?
minus 1.
Minus 46 and minus 0.15. So this suggests that we have some type of negative relationship, right? I said no correlation because when I generated these data, I just said, okay, x is equal to r norm something, and y is also equal to r norm something. So they're just random, right? There shouldn't be a correlation between just random data. There will always, just like when we were talking about the means. We said we'll almost never observe someone that is exactly at the mean. We will almost never get a sample mean that is right at the mean. We're going to have some variations. So the same type of thing. Even though the data should be correlated at all, most of the time you will never observe a correlation of 0 because of sampling error. Okay, so if we had scaled things differently, like we can sort of create something that looks much more spherical. If we had a much larger data set, instead of having 30 observations, we had 10,000 observations, we would have something that would look much, much more spherical. All right. So, let's do our 7th dependent variable.
Negative correlation.
There's a negative correlation.
Yeah.
You're saying
Still not strong. Not strong.
It doesn't have to be. It's maybe 0.
correlation of 0? Well, if you type this in, you should be able to see what the correlation is. You don't even have to guess.
Minus 0.56.
Minus 0.56 something. What did the data look like?
It's curved like
Like that. Like a parabola. Right? So, what did we say about correlations and covariances? We're looking for what? What type of relationships?
direction and strength.
We're looking for strength and direction of a linear relationship, right? Now, is there a relationship between x and y here?
There is a relationship.
There is a relationship. What type of relationship is it?
Curvilinear.
It's a curvilinear relationship. And what type of curvilinear relationship is it?
Negative.
Negative, positive,
Mixed. Negative.
mixed? I'm looking for perfect or imperfect.
Imperfect.
Perfect.
Imperfect, perfect. We have a fight? What is it? Is it imperfect or is it perfect? He says perfect. That's the perfect answer. It is a perfect curvilinear relationship. If I knew what the function was, I actually do know what the function is. I could basically draw, not a line, but a curve that went through all of those data points perfectly, right smack in the middle, right? So there is a perfect curvilinear relationship. But the correlation isn't trying to find curvilinear relationships, it's trying to find linear relationships. So you should have found that there was some covariance, negative 154, and you actually have a pretty, that's not that horrible. You have a decent the line to this, maybe we have something that looks sort of like that. Maybe a little more like that. But we have some decrease, right? For the first part, definitely, this is increasing, but for the second part, it's decreasing. And it looks like we've got more of this decreasing than the increasing, which is why we have the negative correlation. Right? All right, how about this one? D8. It's also negative correlation. We have basically the same thing that we did before, but now it's not a perfect curvilinear relationship, right? So if we figured out what curve best described that, not everything falls on that curve. Things are falling off of the curve, so it's an imperfect relationship. Covariance, negative 136. Correlation, negative 0.49.
The thing is that last class you just gave an example of, let's say, a curve relationship with the no correlation.
Yeah, and for last class when I drew that relationship, I had it like, I tried to draw it like that, where there was just as much going up as there was going down, right? So when there's just as much going up as going down, we really can't fit the line to it. But here, this is still a curvilinear relationship, but now most of it's going down. So we can describe it fairly well with a line. Yeah?
And then it's like more sample size in the left part, which is the positive part.
Huh. So you have more observations that are over here.
Which actually gonna take it more to no correlation.
So this is interesting. And it makes sense sort of intuitively. So you have more data over here than you do over here. And in this part, this is like a positive relation, right? Think about when we were talking about the means and variance and outliers. What effect did an outlier have on the mean?
Not very much. So almost nothing.
But changes. Mean always change.
Outliers had a pretty big effect on the mean. It depends on how far away the outlier is. But compared to things like the mode and median, there's really no effect. But the outlier can shift the mean quite a bit. Now, even though we don't have many over here,
They change.
if we drew a line like this, what we're basically saying is that the mean, if we were to collect all of the data that there are, that the mean, when x is 30, sure there's going to be some variations around that, but the mean of y should equal that, right? And the mean here should equal this. And notice how far away, how far away these are from that. If we went out to here, we're saying that the mean would be like that. Notice how far away that is. It's really, really far away. I'm trying to think, how much do I want to talk about today? Anyway, because that's so far away, what's going to happen is that's going to have a really big pull on things. Now let's imagine this other situation. If we drew a line just like through this section, these are actually a bit closer to here than these were over here. And although there are more of them on this side, they are in general closer. Now remember when we were calculating variance, we were squaring things, right? So if you have small things and you square small things, you get something that's bigger. But if you have something that's really large and you square that, you get something that is a lot bigger, right? So the reasoning is not just the distance, but it has to do with the squared distance. And that is why when we do this, we have the negative correlation as instead of the positive. All right, so let's try to account for the relationship. So before you type this in, why do you think I said this?
New.
You're making a new independent variable.
I am making a new independent variable.
But why we square?
That's my question. Why did we square it?
Variance.
It's not for variance.
Give us new data.
Not it means 0.
No. So if you
Because both are same.
because both x's are the same, huh? Let's think about what we get. Okay, let's think about why I said new IV is our old IV squared. If we said y equals x, or y equals, we'll stop using y, we'll use dv equals IV. What will you get? What does the function look like? I mean, if you were plotting this function, forget about the data. Just think about, in algebra, if you're going to make a graph of that relationship, what does it look like?
Perfect.
It's like this, right?
Yes.
Where these axes are scaled the same? Yeah. Okay, so what if I say dv equals iv squared?
So, I mean, y will stay the same, but x is going to be square root of every x we had in the beginning. So, it's going to shift it like the linear is going to be towards the x.
No, it will be
like
from 0.
or it's going to be from 0 as well.
It's going to be from 0. It sounded like you were on the right
I mean,
track, but I didn't understand the last part.
Whatever you give for independent variable minus or positive, the dependent variable should be positive. So it will be, should be like this.
So this function will look like this.
3.
Eh.
no, it's going to be like
No. This.
It's going to look like this.
No.
Eh. Yes. It's going to look like
Yes.
something like that, right? When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. And 3, it's 9, right? Okay, what type of relationship is that? It's a curvilinear relationship, right? This is not a straight line. It's a curve, right? Now someone said something about 0. What about 0? The correlation for this is 0? It shouldn't be 0.
No.
It should be higher than what we had before. It was positive something?
No.
It
Minus.
should be negative something.
Minus 0.6.
Minus 0.6. Before we had minus 0.5. And now we have something minus 0.6. So it's a stronger relationship, right? We'll talk about that in a second. Why is it stronger?
More negative.
It is stronger. 0.5 or negative 0.5 compared to negative 0.6. You determine the strength of the correlation by its absolute value, right? Negative 0.6, that's bigger than negative 0.5. The closer it is to 1, the stronger it is. This is a stronger relationship. Why?
Because variables are closer each other in plot, their places.
Has something to do with that. So the variables are going to be closer compared to the overall variations. Those lines, if we were going to create the function, yeah, what were you?
The difference is that each x is now x squared.
Yeah, so before we said this curvilinear thing is a function of a line, right? But now we're saying something like this curvilinear thing is a function of something that's curvilinear. Is there a relationship between these two curvilinear things, right? And it's not that great. It's better, but it's still very curvilinear, right? Covariance was huge, negative 20,000 almost. Correlation was bigger, at least in absolute value, bigger, more strength. So, is there anything that we could do to make this curvilinear or a new independent variable that would better fit the data? Let's go back and look at the data originally. So, if we were plotting the squares, it doesn't go down to 0, but x squared is something like that, right? And it's centered on 20, 10, 0, so I should have this shifted over a little bit. But there, right? 20, 0. It should come down there, right? And go back up. So we are trying to explain this with something like this. It's a curvilinear relationship, but where does it change? This changes at 0, right? It goes from going down to all of a sudden now going up. This, where does this seem to change? At about 50? So at about 50, so we go up to 50 and then down basically thereafter. Do we want to pick a different value? From eyeballing it, to me, I picked 52. So, go ahead and create this. It's a new independent variable. And what it is the independent variable minus 52 squared. Basically what we did is, we didn't only create a curve data set for the first, we also shifted it, right? And what do we find for the covariance?
Minus 4,700.
Minus 4,700, so that's smaller. So you might think that the correlation is going to be smaller. But if you look at the plot, if you look at the scatter plot, you think, oh wow, this looks like it's fit pretty well. And so what's the correlation? Minus 933 something? Or minus 0.9? Okay, so let's get back to her question, which was, why is it negative? Why is the correlation negative? Why isn't it positive?
Because x increases, y increases.
Yeah, if we went back to the original data, we have something that's going like this. But the x squared goes like this, right? So what's the relationship? Well, as this is going down, this is going up, right? As this is going up, here it's going up a little. Oh, here it's going down a little. Here it's going up a lot. Here it's going down a lot, right? When you have one thing that increases and the other thing decreases, what type of correlation do you have? Negative. So when this is increasing, this is decreasing. And when this is increasing, that's decreasing. That's a perfect definition for a negative correlation. Does it make sense now why this is like that? So what if, I mean, we made our transformed independent variable something like this, right? What if we did one last, oh, good grief. TIV stands for transformed independent variable. All right. What if we put parentheses around this and made that negative? What would happen? Positive what?
Correlation.
Of what? What's the value?
Same, but sign is different.
Same, but the sign is different. How about the covariance?
Same,
It's the
sign.
same, but the sign is different, right? Cool. So what just happened? Well, originally we were trying to fit a straight line to a curvilinear function, right? But when we transformed our independent variable, we had a better model, right? We had a model where we had some curvilinear function that was trying to fit this curvilinear data. And what happened as a result? Well, we had a pretty good linear relationship between those two curvilinear things, right? So on Monday, we'll learn how we can find the best models without trial and error. I'm not sure if 52 is the best, or if 51 is the best, or what. On Monday, we'll see how to do this. Very, well, I was going to say very simply. It's simply when you let R do it. On Monday, I'm not sure if we'll do it with R. Anyway, next lab, we will talk about regression.